Now today we begin with the illustrations. Okay, the first illustration here is given very easy. Just we have to utilize the equation and we put the value. What speed should a galaxy move with respect to us, so that the sodium line at 589 nanometer is observed at 589.6 nanometer. So this 589 is observed at 589.6. So delta lambda, change in the wavelength or shift in the wavelength, we can say that delta lambda is easily found here. Lambda prime minus lambda final wavelength minus initial, that is 0.6 nanometer. Okay, now the equation which is given here on say page number 359, just we have to utilize. Okay, that is delta nu as such. Delta nu upon nu is equal to the velocity, radial velocity upon velocity of light, only magnitude. Now see, if you replace this delta nu upon nu as delta lambda upon lambda, okay, because v is equal to, rather velocity is equal to frequency into lambda, therefore this can be replaced. Okay, so the equation can be written as delta lambda upon lambda is equal to velocity upon the velocity of light, that is c. Here this velocity, that is a radial velocity. Okay, it is nothing but the velocity of the source. Okay, now that velocity of source we make as a subject of formula. Then we have this v is equal to c into delta lambda upon lambda, and you just have to place all the values here. C is known to us 3 into 10 raised to 8 meter per second. Delta lambda we got 0.6 nanometer, so 0.6 into 10 raised to minus 9, and original wavelength is 589, that is lambda. Okay, if you simplify this, then you will get 3.056 into 10 raised to 5 meter per second, or it is approximately 306 kilometer per second. Okay, now example number 10.3. Two slits are made 1 millimeter apart and the screen is placed 1 meter away. What is the fringe separation when blue green light of wavelength 500 nanometer is used? Okay, so the light is used as a which is having the wavelength 500 nanometer. Now the separation is lambda capital D upon small d. Okay, just we have to place the value. Lambda is 500 into 10 raised to minus 9 capital D, that is where the screen is. Okay, screen is kept how much away? It is kept 1 meter away, so capital D is 1. Okay, and D is 1 millimeter, 1 into 10 raised to minus 3, so it is placed here. Okay, and just we have to simplify. Okay, beta you will get 5 into 10 raised to minus 4, that is the distance, or rather the fringe separation, distance between two fringes. Okay, now in example 10.3, that is a previous example, what should be the width of the each slit? Okay, or what should be the width of each slit be to obtain 10 maxima of the double slit pattern within the central maximum of the single slit pattern. Now see, for diffraction there is a single slit and that is having the width of say small d. Okay, here width of central maximum is given by 2 lambda capital D upon small d. Now For stationary interference pattern, there are two slits. Okay, for interference, there are two slits with separation of say d prime. We consider that separation between the two slits to obtain the interference is d prime. Here, total width of 10 bright fringes will be 10 lambda capital D upon d prime. Okay, because one is having the width that is lambda capital D upon d prime, so 10 will have 10 into lambda capital D upon d prime. Okay, now the statement which is given to us, or the condition which is given to us, is that this width of the central maximum of the diffraction is 10 times the width of the different fringes which are there in the interference. So we can write this first equation is equal to second equation, or we can say 2 lambda capital D upon D is equal to 10 lambda capital D upon D prime. So you can easily calculate now this lambda D can be cancelled out. Okay, this lambda into capital D can be cancelled out. Okay, and this becomes 2 5s are 10. So we can have d prime is equal to d upon 5, that is 1 millimeter upon 5, because this d is given to us 1 millimeter. So d prime is 0.2 millimeter. Okay, here we have to keep in mind that d prime, try to understand the value d prime is the separation between two slits in the Young's double slit experiment. It is not the width of any one slit. So d prime is the width, or is not the width, but it is the separation between two slits in the Young's double slit experiment. Okay, this we have to keep in our mind. Now, example number 10.8, discuss the intensity of transmitted light when a Polaroid sheet is rotated between two crossed Polaroid. Okay. Now, situation given in the statement is shown in this figure. Say for example, this is the incident light here. Okay. So incident light is coming from this point, and this is the first initial, say P1, P2 and P3 are the three polarizer which are placed successively with their pass axis in the vertical plane. Now see, P1 and P3 are crossed. P1 and P3, they are crossed. Angle between their optical axis is pi by 2. Crossed means the angle between their axis is pi by 2. Now in this situation, if angle between A1 and A2, that is first and second axis, is theta, then angle between A2 and A3 will be pi by 2 minus theta. Okay, if the angle between first and second is theta, then between second and third it will be pi by 2 minus theta, because these two are at right angle, or their optic axis are at right angle to each other. Okay, now as you know that intensity which is coming out of the Polaroid is given by I is equal to I0 cos square theta. This is Malus law. Okay, now intensity of light which is coming out from the second plate is given by, say, I2, and I2 is equal to I1 cos square theta. Say for example, here the intensity of light which is incident is I0. Okay, here the incident light is having the intensity I0. The intensity of light which is coming out from the first tourmaline plate or first Polaroid is I1, and this I1 is incident on second Polaroid. So what happens, the light which is coming out here from the second is having the intensity, say, 2. And according to Malus law, because these two axes are at an angle theta with each other, the intensity of light which is coming out here from the second, that is I2 is equal to I1 cos square theta, where I1 is the intensity of light incident on this second plate. Okay, I1 is the intensity of light which is incident on the second plate. So I2 is the intensity which is coming out from the second plate is given by I2 is equal to I1 cos square theta. Okay, now if I take I1 is equal to I0, okay, then instead of I1 it is written as I0, so it becomes I0 cos square theta. Say initial intensity we take which is coming out is I0 cos square theta. Okay, similarly intensity of light transmitted by the third plate, that will be equal to I3, and I3 is equal to I2 cos square pi by 2 minus theta. Now I2 is nothing but I0 cos square theta, and this becomes cos square pi by 2 minus theta, and cos square pi by 2 minus theta is nothing but sin square theta. Okay, so cos square pi by 2 theta is written as sin square theta, and cos square theta is 1 plus cos 2 theta by 2. Sin square theta is 1 minus cos 2 theta by 2. Okay, so this simplified, or we can say it can be simplified easily now. It is 1 plus cos 2 theta, 1 minus cos 2 theta. So it becomes 1 minus cos square 2 theta upon 2 into 2 will become 4. Okay, and this becomes sin square 2 theta. Okay, 1 minus cos square 2 theta will become sin square 2 theta, and here coefficient can be I0 upon 4. Okay, so in above figure, when P2 is rotated in vertical plane, okay, theta will change, and hence I3 will change as per this equation number 2, because as theta changes, okay, this I3 also changes. Okay, so as theta changes, the intensity which is coming out from the third plate also changes. And you can also understand that when theta is equal to pi by 4, try to understand, when theta is equal to pi by 4, instead of this theta, it is 2 theta rather. So if you take theta is equal to pi by 4, then what will happen? This sine pi by 2 it becomes, and sine pi by 2 is 1, and at that time the intensity which is coming out from the third plate will be maximum. Okay, that will be equal to I0 by 4. Okay, that intensity will be I0 by 4, maximum intensity from the third plate when theta is pi by 4. Okay, now unpolarized light, this is your last example 10.9 as such. Okay, unpolarized light is incident on a plain glass surface. What should be the angle of incidence so that the reflected and refracted rays are perpendicular to each other? Whenever the reflected ray and refracted ray are perpendicular, then we can say the reflected light is plane polarized, and you can use this formula tan theta b, tan theta b, Brewster's angle. Sometimes it is also denoted by theta p. Okay, so tan theta b is equal to the refractive index. Okay, that is equal to mu. Okay, so mu is equal to tan theta b or p, whatever. So tan theta p is equal to 1.5. Here the value of the angle is, say, it is 56.19. Unpolarized light is incident on a plain glass surface. Try to understand, glass surface. It means the refractive index is 1.5. So tan theta b is equal to 1.5, and if you see in the natural tangent, Okay, then that angle is about 56 degree 19 minute. Okay, 56 degree 19 minute will be the angle, that is theta p, angle of polarization. Okay, so here this theta p is about 56 degree 19 minute, or if you want to write in decimal 56.3, it can be written as, but this is a correct value, or this way also it can be written. Okay, so here our examples are getting over. Try to write this 2-3 times in the notebook and practice. Okay, thank you very much.